We are working through this guy here. It's chapter 2, bell-shaped data. And I want to get this section as close to being finished as I can today. We'll have to see how things go, whether or not that happens. So, bell-shaped data is data that has this shape. It looks like a bell. I would call it hill-shaped data, but I'm not in charge of the names. Suppose there was a town, and the population of this town, all I know about it is that the mean age is 35 and that the standard deviation was 10, and that it's bell-shaped data. Then you can set up this standard bell-shaped curve, and right in the middle, right in the top, is the mean. And we use X bar for that guy. Now, since the standard deviation is 10, this guy is 45, this guy is 55, and this guy would be 65. Take 10 away and you get to 25. Take a standard deviation of 10 away, you get that. And take another standard deviation of 10 and you get that. And then if you add some little lines like this, hopefully you can remember this picture. Wasn't there an interesting property about 1 standard deviation, 2 standard deviations, and 3 standard deviations away from the mean? Because what that allows us to do, even although the only thing I know is the mean and standard deviation and it's bell-shaped, I can tell you between here and here, which is 1 standard deviation, 68% of all the town population will live there. So a homework question would give you this information, and then they'd ask you, about 6% of town population are aged, and the answer is, are aged between 25 to 45. And then if you do 2 standard deviations, right, which is here to here, 95% of everybody in that town is in that age group, and that is from 15 to 55. And then if you do 3 standard deviations, you get the last one, which is 99.7. And that starts at what, 5 and finishes to 65. I've actually seen this table in the way I've created called, believe it or not, and I'll write it down and you can go and check it. It's called the 68, 95, 99.7 rule. I kind of like that name because doesn't it tell you everything you need to know? The 68, 95, 99.7 rule. It tells us that all bell-shaped data follows that rule. It's called the empirical rule. That's another name for it. Now, based on this town, I would, looking at the spread, there's not an awful lot of very old people in this town, right? You know, 99.7 is in that range. Isn't there only, what, 0.3% in total that are really young or old? And that 0.3%, right, the 0.3% is equally spread. So basically about 0.1.5% either side. Look at how few children, babies, there are in this town. And look at how few old people are in that town. So if I was trying to figure out what that town might look like, can you imagine down in California, you've got one of those Silicon City towns where everybody works for a high-tech computer place? Can you imagine that there are probably a lot of people there, you know, in the young age group, right, the 35s, whatever, and they haven't really started their family. And when you get old, you can't afford to live there, don't you? Take your pension money and sell your house and go somewhere else. And that's what that town would look like. Now, I've created a different town here, and this town is going to be in Florida. So this one would probably be in Silicon Valley in California. This town is in Florida. Does anybody know why I'm picking Florida?
Isn't it like a retirement? Most people there when they...
Yeah, so I've deliberately picked one. I'm making the numbers up, but here goes. Average age of 50. That's pretty old because it's a retirement community. And the standard deviation is 15. So 65, 80, 95. Now going this way, you've got 35, 20, and 5. So if I use the 68, 95, 99% rule, can you see that in that range, the 35s to 65-year-olds, and then this range here, that's 2 standard deviations, that's 20 to 80, and then this range here, you get 5 to 95. Do you feel comfortable if I told you a story about a place and I said the mean was 50 and the standard deviation was 15, or any mean or any standard deviation? Do you feel comfortable you could create this bell-shaped picture and you could answer the 68, 95, 99.7? Do you feel comfortable about that type of question? Okay. Now, that's kind of impressive to me, that if you know the data is bell-shaped, all you need to really know is the mean and standard deviation, and you've pretty much got the essence of what that data looks like. Don't you get an idea of how spread out it is, what kind of range the middle 68% looks like, and then growing outwards to 99.7? And in particular, as an added little bonus, don't the outliers live outside the last number? Because isn't that 3 standard deviations away on both sides? And if you're bigger than 3, you're an outlier. And if you're less than 3 standard deviations from the mean, you're an outlier. So you even get to know who are the exceptional outliers, either old or young, or high or low, depending on the story. So far, so good? Right. Now I'm going to show you a more complex version of that same thing. So I'm going to do IQ scores because that gives me nice, easy numbers. The average IQ, right, is 100, and the standard deviation is 10. And I'm going to do the 68, 95, 99.7% bell-shaped thing, but I am going to add some information to it. So this is 100. This will be 110. This will be 120. And this will be 130. And this will be 90. This will be 80. This will be 70. Now, normally, I would say from here to here is 68%. Agreed? That would be the usual start. But I am going to do something a little different. That middle chunk is 68%. Agreed? Because of symmetry, doesn't that make this piece 34 and this piece 34? Do you agree? 68 split down the middle. So actually, I can get a little bit more information. Can I tell you that 34% of all the data is between 100 and 110? So 34% of Americans have an IQ between 100 and 110. And also 34% of Americans have an IQ somewhere in the range 90 to 100. Now, the next one gets a bit messier. If you go 2 standard deviations either side, the answer to that is 95%, right? Now I'm going to have to put this thing over here for a minute because I'm going to be doing a whole load of scribbling. From there to there, 68%. And we've just used from there to there, is 95%. I'm going to figure out how much that little piece is and how much that little piece is. And once they've figured it out, it's probably a good idea just to write down this guy here on a separate piece of paper and just have them handy, right? So you can use them in various questions that do that. So let's figure out how that works. If you take 95 and you subtract 68 from it, you get 27, agreed? Oops. So aren't those two shaded bits 27, right? And isn't each one of them the same size? So shouldn't each one of these be half of 27? And that's what, 13.5%. So that is how I figured out that this little piece is 13.5 and this little piece is 13.5.
Where did you get the 2
Are you
percents from?
Where did I get the 2 13.5 from?
No,
Is that your question?
34s, or 34.
Oh, yeah, take 68 and half it, and you get 34 and 34.
Wait, then how did you get 68%? Did you just...
Oh, the 68% comes from the empirical rule that says one standard deviation either side of the mean is always 68.
Oh, okay. Got it. Thank you.
And so I know that's 68 because it's always 68. And now I split it into 2 34s. And I know this is 95. And with a little bit of jiggery pokery, I figured out that these two pieces, and I just mean, you know, this little piece here and this little piece here, these are 13.5s and these are 34. I bet you if you add all of those four together, shouldn't they add up to 95? And they do.
Okay.
Now it's going to get even messier for the last one. That's this one here. Well, it's the second last one, technically. I know that when you go from here to here, it's 99.7%. But I already know what from here to here is. It's 95%. Now, what I'm going to do then is I'm going to figure out how much these two little pieces are going to be. And it's the same kind of thing I did here. Don't you take the 99.7%, 3 standard deviations, and you take away the 95%, that middle chunk, and that leaves me with what, 4.7? And then you share it equally, and you get 2.35%. And that's how I got 2.35%. Now, once I've finished this, I'll show you why this weird looking table is going to be so helpful in the future. Okay. Technically speaking, shouldn't I find the last little pieces? Because there are some bits left over, right? When you do 3 standard deviations, oops, it's went green. You haven't covered everything, right? You've only done 99.7%. So isn't there 0.3% unaccounted for? Isn't that what's left in the edges? And half of each, right? So if you do 0.3% and you half it, you get 0.15% on each side. And this is like the ultimate version of what that table looks like. Not only do I have the 1, 2, 3 standard deviation numbers in it, do you see I even know little pieces? I can tell you, for instance, that only 2.35% of Americans have an IQ between 120 and 130. Okay, now, how can that be used in answering some questions? Well, I'm going to find a question that basically uses. I think there's 2 of them. There might be 3, but definitely there's 2. And as soon as I find it, I'll tell you the number so you know where to go looking when you do it as well. Question 13. And in this question, the mean is 58 and the standard deviation is 2. And it says use the empirical rule. Can we, when you see that, it means use this guy, right? So when you see use the empirical rule, they're talking about this guy. Now we're going to use the empirical rule and to answer some rather strange questions. This is the first one. What is the head circumference So I should have basically told you that this data is head circumference of adults. So you might, and I didn't know this, but you know, if you take your head and you put a tape measure around it, evidently 58 inches is the average head circumference for an adult male. And the standard deviation is 2. So if you think your friend is big-headed, get a tape measure out and find the circumference, and you might be able to find out how big their head is. So what is the head circumference such that only 2.5% of adults have a smaller one? You know, I could have made that sentence 10 times shorter. How big does your head have to be so that you're in the bottom 2.5%? Wouldn't that be the equivalent question? How big of a head do you need to be in the bottom 2.5%? Well, we're going to create this table. And we start at the center, which is 58, and we go out. So what's that? 60, 62, 64. And then 56, 54, 52. And since I've already got these percentages here, I'm not going to fill them in here. I'm just going to cheat. So can you imagine these numbers are these guys, right? Right, let's look where the bottom 2.5% are. Would you agree 0.15% here? If you add this piece to it, doesn't that get you the bottom 2.5%? You agree? The bottom 2.5%. Where is that? That number there is him. So your answer, 54. Okay. I want to know what height circumference-wise do you need to be in the top 16%? Okay, if you look at this table, where does the top, right? It's this guy, this guy, this guy, this guy, right? How far along do you go before you get to the 16%, guys? Well, let's see. 0.15, if you add that, you get what, 2.5? If you add that one, can you see it's here? Everybody here? And what's that guy? Oh, that's just one circumference, so we'll talk about that one. So if you have a friend you think's got a big head, measure it. If it's 60 or bigger, your friend is in the top 16% of American adult male heads. Are we okay with how this thing can be used? It's a little bit clunky. I know it's not the best way of tackling the question, but you can use it for the top 5%, the bottom 16%, the top 16%, things like that. So the questions that do it are 13, so you know which one you're going to do this to. And question 14. So those two questions use that, right? So it's a lot of work for only two questions, right? That's the only two that do this. Any questions before we move on to our next topic, which is going to be Z-scores? Okay, we're good. The full title is Standardized Z-scores, but everybody just calls them Z-scores. And what Z-scores are typically used for is to compare two results from two different samples, to see if there's how to compare them, to see if there's any way of deciding which is better than others. So I'm going to give you a kind of story and to show you why Z-scores can be helpful. We're going to have two people, Mary and John. And Mary and John went to university and they both took a math class, right? The same math class. Mary went into one class, we'll call her class A, and John went into a totally different class B. And in Mary's class, the professor was very generous, right? He was quite nice on his exams and pretty lenient on mistakes. And in her class, the mean was 60 and the standard deviation was 20. John, he was in a much more rigorous class. And in his class, the average was 50 and the standard deviation was 10. Now, after the final exam, Mary got a score of 75 and John got a score of 65. And they were both arguing about who done better. And Mary would say, well, my number's bigger than you, right? I got 75. I did better than you. You only got 65. See, I did better than you. But John said, yeah, but it's dead easy to get 75 in his class. Anybody could get 75 in his class. It's really hard to get 65 in my guy's class, right? Do you see that it's not fair to use just the score when you want to compare two people when the means and standard deviations are different? Would you agree it's harder to get a score when the average is 50 and the standard deviation is quite small? It's a lot easier to get a high score when it's a big average and the standard deviation is high, right? It's easy to do that. So we need a way of taking this and standardizing it. And what that allows us to do then is it'll actually allow us to unbiasedly decide which one of these actually did better. Have you got a gut feeling? Do you think it's Mary that still wins? Do you think John did better? Do you think it's a draw? Do you think they're equally good? What's your gut feeling? Evidently you don't have a gut feeling. Last chance, anybody want to throw in 5 cents worth and say, I think it's John or I think it's Mary? Right, here goes. Well done. You're right, by the way. This is the formula for calculating the Z-score. I'm going to give you the English version, then the math-like version. In the English version, it's data, take away the mean, divided by the standard deviation. So when you do this calculation, you will have found the Z-score for Mary and then the Z-score for John. It's X, take away X bar over S if you want to do the Z-score formula and do it more mathematical, right? This and that are equivalent. Can you see that mean is called X bar and standard deviation is called S? And the data, well, the data is going to be 75 when I do Mary, and it's going to be 65 when I do John. So let's find the Z-score of each person. So this is going to be the Z-score for Mary. Well, she got 75. Take away the mean, which is 60, and divide by standard deviation of 20. So that's 15 divided by 20. That is, oops, sorry about that. That's 0.75. Okay, and let's see what the Z-score for John was. Well, the Z-score for John was he got 65. And the average was 50. And the standard deviation was 10. And that's 15, but divided by 10, it's 1.5. So it is much more difficult to get a 65 in the class that John was in compared to the class that Mary was in. Now, if you're a student and you go to university and you talk to people, they might say to you, oh, go to the class that Mary's in. It's going to be a lot easier to pass that class, and it's going to be a lot easier to get a 4.0 in that class. If you go into that other class, I personally didn't have this, but I do know students who've told me that there was an English professor that they had who never, ever gave 100% on any assignment. Right? You could get 99, but he would never give you 100. And his argument was, nothing is perfect. Bit unfair. Do you know you can get 100% in math? Because can't you be perfect in math? I mean, if the answer's 42, it's 42, right? It's perfect, right? I'm just ranting on for a few minutes, get it out of my head. Me and English were not friends at school. Didn't like English. I didn't like especially writing essays. Not that I couldn't write essays, I kind of enjoyed doing that. But I would always give an essay and I'd get a grade. And I thought, when I did my essay, because I'm arrogant, I thought my essay was a great essay. This is an A essay, or this is definitely a good essay, right? And then I get it back and it's a B. And I can handle that up to a point. And so you would go and ask, or they'd write down at the side. And isn't it very subjective sometimes, English? Like, your arguments could have been clearer, or you could have done this differently, or you could have emphasized that more. And it's kind of wishy-washy. I always found English to be very, very subjective. Now, if you told me I got 5 words and I misspelt them wrong, and 2 commas were missing and 1 was in the wrong place, and you added or took points away according to that, I can live with that, because isn't that a rule that I can understand? But I can't understand subjectivity of it could be better, it could be more, it could be clearer, it could be precise. Those are very, very wishy-washy words. And it always frustrated the heck out of me. And so one of the reasons I love math, isn't it nice when the answer's 42? Because it's 42 and it's right. And if it ain't right, there's a reason why it's not right. And we can tell you about it. Now, that's my personal thing. You might actually love English because of the flexibility that it has. Right, back to this story. How would a university fix that? It is true that in some universities, they standardize the scores. So what that means is it doesn't matter how hard or easy the grading is. you will still get an A at the same level in each class. Now, how do they make that happen? Dead easy. The score that the person gets isn't the one that's used for the grade. Here's a grading system. If you get a Z score that's bigger than 3.0, you get an A. And if you get a Z score between 2 and 2.9, I'll give you a B. And if you get a Z score of 1 to 1.9, I'll give you a C. Can you see then that you can assign A, Bs, and Cs without any real hassle? Because won't the A, Bs, and Cs be the Z scores, in which case it's already factored out how easy the grading system is. And that's why it's sometimes called the standardized Z scores. You might not know it, but do you know the SAT exams? They're standardized. You might have got a raw score of 590, but they standardized it when they give you your score back. So that if one year the SAT was harder than the previous year, that gets factored out. So SAT of, I'm making up numbers because I know the numbers. An SAT of 590 is the same value as an SAT 10 years ago at 590. No grade inflation, nothing. And they do it by standardizing. I think that's kind of cool. Are we happy about how to calculate Z scores then? It's data, take away the mean, over standard deviation. So there are a number of questions where you are being asked to do that. I'll give you a list of them so that when you're doing your homework, and I'll pick one as well. Here we go. Questions 5 and question 6 ask you to do that. So I'm just going to pick a question at random. This is question 5C. In this question, it's the mean weight of men, and it's 170 pounds. And the men, the standard deviation is, come back to me, 20. And in question C, they ask you to find out what the Z score would be for 180 pounds. So the Z score is data, take away mean, divided by standard deviation, and I believe the answer to that question would be 0.5. Pretty straightforward, right? You got a formula, you plug the guy in, you get a number, a decimal typically. Question 6, very similar. Let's move on, case I mind. No. No. Okay, I think that's there. That is the 2 questions that deal with calculating Z scores. Before I leave, do you know if you take a bell-shaped data, right? You collect people's ages or whatever you did. Can you imagine collecting 200 people's ages and you got that data that we talked about in Florida, right? Right, bell-shaped. If you take every single person and you turn them into a Z score, right? So imagine the 42-year-old get turned into a Z score, the 90-year-old get turned into a Z score, you get a bell-shaped data. Right? Now, what Z score does somebody who has the average mean get? What would the Z score be if somebody weighed 170 pounds, for instance? Be 0, yes. So let's move. Think about it. The Z score is data, take away the mean, over, I'll call it ST for short, standard deviation. So if you are the mean, won't you have a Z score of 0? Now, the table looks something like this. Why do the z-scores only go 1, 2, 3? Why isn't there a z-score of 20 or something? Why is this always the shape that you end up with, no matter what data you start with? Well, it's kind of interesting. Although I haven't told you yet, do you know a z-score of 1.5? It means you're 1.5 standard deviations away from the mean. So what the z-score is measuring is how many standard deviations you are from the mean of that population. And when we did empirical, wasn't it 1, 2, 3, and that was the end of it virtually? One standard deviation gets you a ZA1, then a ZA2, and a ZA3. I think that's interesting. So we now have a way of comparing scores, heights, weights, whatever you want, of two disparate groups of people. And we can find out how likely, which one of you did best in a test or whatever it might be. And it's factored out everything except the essence of how hard it is to get there. There is one question I just remembered about. I'll better find the question because I'm not 100% sure I remember the details of it. Okay, this question is number 9. And it says, if you learned that your score in an exam was 83, and the mean of the exam, so that's your score, and the mean of that exam was 69, and it asks you a strange question. Would you be more satisfied if the standard deviation was 7 or if it was 20? Right, so you got 83, good score, better than the mean, you're feeling happy. But would you feel happier if the standard deviation was 7, which would mean getting 83 is really hard, or if the standard deviation was 20? Which one of those would be the one that you would prefer because it meant your 83 was even better? I think I couldn't hear what you said, but you definitely said something, David. This one? Agreed. And you might say, well, why is that one good? Well, if you can imagine 69 and going up in 7s, isn't 83 going to be way up here somewhere? But if you did 69 and you went up in 20s, okay, you did okay, but you see there's a lot of other people who probably did better than you. And, here's the question. Actually, yeah, we'll get these questions over. I didn't quite finish this section. There's one little bit that we'll do tomorrow and then I will be finished it. Right, we've got a mean of 50. Right? And the standard deviation is 12. And I want to know what the range would be. And is there a way to find it? And I'm not talking about the exact range, but an estimate of the range. And I also want to do an estimate of the standard deviation. So can you imagine there's 50 and you go up and go down the usual 3. So you would go, what, 62, 74, 86, and then you'd go back 12, so 38, back 12, 26, back 12, 14. That would be your basic shape, right? Now, if I want to estimate the range, I know that there's people over here, and I know that there's people over here, but there's very, very few of them, right? So if I had to estimate the range, do you see I would take 86 and take away 14. And so I would estimate it's about 72. Now it will be a little bit out, but won't it be in the ballpark figure area? Because the chances are, isn't there probably only going to be one person here and maybe one person here, right? So it's not going to be that far out. Now, what about estimating the standard deviation? Well, I'm going to use there to there again, which we already know is 72. Great. Now, 1, 2, 3 standard deviations, 1, 2, 3 standard deviations. Doesn't that represent 6 standard deviations? Right? From here to here, 1, 2, 3, 4, 5, 6. So shouldn't the standard deviation just be the range divided by 6? So my estimate for the standard deviation would be 12. So this table that we've got, it can be used for all sorts of things. Estimate the range, estimate the standard deviation. Z-scores are helpful for comparing two scores and seeing who's harder to get, who's easier to get. Doesn't really do too much yet apart from that. And say hi and bye-bye. We're finished.
I actually had a question on the homework.
Sure, you hang about, I'll answer it. I
Okay.
can do it right now if you want, but I was
Yeah.
going to do it at the end. Yeah, what you got?
So it's on the types of variables.
Okay, what section is that, David?
Chapter 2, types of variables, homework. I think it's just maybe the first assignment after like the introduction thing.
Gotcha, found it. Okay.
And then it was my question. Oh, what question was it? Well, I just lost it. Question 9.
Okay. Okay, so it's second last question according to what I can see here.
Yeah, and it's the, is it the same question for everyone? I feel like some of them, like, is it the
Most of the
board
time,
use?
it's a different question. If you see red numbers or red anything, that indicates it's changes from one person to another. Well, that's what I say. I don't know if you get to see red numbers. Do you see red numbers sometimes?
Well, not red numbers. It's red because I ended up getting the question wrong because I couldn't get it right. But,
Oh, no.
I think that's different than
Question
what you're
9
talking
doesn't have any red numbers, so that makes it everybody gets the same question, which happens sometimes. So
Okay.
I'm going to show you that question. And I've got what they have as the answer, and then we're going to have a look at their answer and see if we can agree with it. So about 70, I'm assuming this is the same question, right? About
No.
75%.
It's not.
Okay, this is question 9 from, well, where's the top? I'll scroll up because evidently I can't find the edge. Oh, there's the edge. I can find it now. And this is
No,
exploring.
No, it's not that one. It's the types of variables, the one above the exploring. Yeah.
Okay, gotcha. Right,
And
that
then
was my
question 9,
fault.
yeah.
Right, so I'll do question 9 once this loads up. And question 9 isn't, it's quite early on. Okay, can you see the answers I've got here before I do it, or will I have to go out and in and
Yeah, I can
look
see
at
your
it?
answers.
Okay, this is their answer. So for each of the following situations reported in the news, specify what variables were measured on each individual and whether they are best described as categorical, ordinal, or quantitative. Right.
So I'm specifically asking about B.
Okay.
And
So,
I thought it was like all of them minus, well, I don't know. It's only saying 2, but I don't understand why it's just the 2.
okay, so let's go to the top one and see why we might not use that. Whether a person uses either one of the 2 major coaching programs or not is categorical data. Okay, let me read this story then. According to College Board News, students using either one of two major coaching programs were likely to experience an average gain of 5 to 19 points on verbal and 5 to 38 points on math. So what happens here is that they have two different coaching programs. I would probably call them tutoring programs, right? So one might be one-to-one with a professor, and the second one might be software that you go to, and it talks you through the solutions, right? As an example of two programs. Now, the first thing is whether a person uses either one of the two major coaching programs or not is a categorical variable. Well, I guess you might think that's true because I thought it was originally. But in this story, you are doing one and only one. You don't have a choice.
Okay.
So it's not really giving you the choice, so you can't have the choice. So it's not really a variable.
Okay.
If
Makes
it was a
sense.
variable, I'd agree it's categorical. But in the way this story, the way I'm reading this story is you're doing A and the other guy's doing B. You don't have a choice. If there's
Okay.
no choice, it's not really a variable. Right? Whether a person had gains on the SAT or not is a categorical variable.
Yeah, I got this question wrong.
Yeah. That one feels like me in English again. This feels like there's a lot of what does it mean? I'm trying to get into the head of the person who decided this is not one, and the only argument I can give, and I'm not even convincing myself, but it's the argument that's coming in my head, is that in this storyline, you take the tutoring and you get a gain of 4, right? Somebody else takes the software and they get a gain of 5. Whether you get a gain or not is not really a choice here. You take the thing and you get what you get. Not really convinced by my argument, but that's the best I can come up with. And sometimes, and I will guarantee this, I will disagree with the answers that they've got. And I probably would have disagreed with that one, but we'll live with it. You're happy with this one, so we won't go through that.
Yeah.
Verbal SAT score is a quantitative variable. Yes.
Yeah.
Yeah.
I thought it was.
It is. You get 42 or 79 or whatever, you get a number. The only way, and I'm not going with this one, I'm disagreeing with them. I'm picking that one too. The score that you get is a number that measures something. No, it's still a number. I can't argue against it. My brain refuses to, and I refuse to. We're just going to disagree with them. I'm picking that one, and I'm picking that one too.
Yeah.
Megan, you look like you've done this. Did you have the same argument? Did you just disagree with them and wanted to pick those two? Yeah. I can't help it. It's software, right? Evidently, the guy who wrote this question, and guy means male or female, by the way, the guy who done this decided that it wasn't for whatever reason. They might be thinking, oh, God, yes. I just came to me what he might be thinking. Is shoe size really a number in the usual sense of things?
No.
I'll tell you what I mean by that. If you have a shoe size of 4 and a shoe size of 8, is your feet twice as big as a 4?
No.
Aren't those more labels rather than truly numbers? Another example, isn't your social security number a number? But technically speaking, isn't it really just a code or a label?
Mm-hmm.
Right. So there is a way that you can figure out whether a number is truly a number or a code. Because if it's a code, it's categorical. It's a bit like me saying ugly people are 1, okay people are 2, and pretty people are 3. I'm using the numbers 1, 2, 3, but aren't they just labels? It's really categorical behind it all, right? Imagine you collected a whole set of data and you found the average. Does the average make sense? And if the answer is yes, that average makes sense, you are looking at a number. And if the average doesn't make sense, then you're looking at categorical data where it's just coded with a number. So examples, if you went to a football game and the first 5 guys who left the field, if you took the average of the numbers on their back and you got 12.2, would those numbers mean anything sensible? That's because aren't the numbers just codes for the guys?
Yeah.
He's number 42. It's just a code. If you took 20 people's telephone numbers and averaged them out, would that average telephone number mean anything? No, because telephone numbers are actually codes. Couldn't you have had a telephone number and they do it? Couldn't they have AACCDDD? Couldn't you give your telephone number using letters? Right. How about take an obvious number one. You did 5 tests and you found the average, and the average was 82. Wouldn't that average make sense? That makes it numerical, doesn't it? Quantitative. So I wonder if he is thinking, or she is thinking, that the guy is thinking the SAT scores are codes rather than real numbers. Now, I don't think they are codes. I think they're real numbers. And that's why I'm still going with they should have been counted.
Okay.
Right, that's a little bit, what's the word I'm looking for? A little esoteric, isn't it? That a number might not really be a number. It could be a code.
Yeah.
Right. What about this one? Were you happy with leaving this one out?
Yeah, that's the one that I didn't mark.
Yeah. See, and that's what's bugging me, because if the gain is quantitative, how come the guy you started with isn't? You know, that doesn't make sense. You agree?
Yeah.
If your gain is a number, surely the things you had to be numbers, because how else could you have a gain that's a number?
Right.
Yeah. So I don't even think that they are being consistent with their own measuring system. So I totally agree with you there. Do you just want to pick the 2 that they got so you can get the points, but argue that they're just wrong in your brain?
I tried the 5 different times.
Too many shots.
To try and get
what you do,
answers.
David, dead easy. Not a problem. What you do, David, is you shoot me an email, because I'll forget, and I'm going to be doing a class in a little while, and I just go back and I give you the points and call it good.
Okay.
So Megan, did you get the right answer, for instance, eventually? So you shoot me an email and you'll get the points, right? You didn't get that wrong because you were wrong. You got that wrong because the answer was wrong, right? That's a totally different kind of wrong.
Well, I appreciate
and that goes for anybody who is unsure that, you know, you believe you were correct. I think when the answer is a number, we can be pretty safe that it should be that number, but not this question. Is there anything else, David?
No, that's it. Thank you.
Okay, anybody else got some questions that they want me to do right now while you're here? Okay, David, do you, oh God. I'm going to make an assumption, and David can tell me it wasn't any good. Can I keep this as part of the lesson so that when people go back, they can see, you know, that sometimes the book's wrong? Is it okay for me to do that with you guys? I guess I should have had David's permission, and I will try and remember. I will ask David tomorrow for his permission, right?
I think I got that one wrong too. might have just skipped over it and haven't gone back to fix it, but I think I guessed.
Right, if you want to go back and fix it, it's the third one and the last one.
Yeah.
So just do their answers and call it good.
I think it.
If you run out of shots like Megan does, she's going to shoot me an email so I can give her points. Megan, can you, is it Megan or Megan?
Megan.
Megan, right. So Megan, what you need to do is shoot me a little email as well so I can give you the points. But you've got another job. Tomorrow you're going to say, ask David for permission and remind me this so I can tell everybody else. Because I'm sure if there's 2 of you, there's probably 20 of you, right? And you all want to get your points. And that is us, I think, unless there's other questions. Okay, bye-bye for a second time then, guys.